welcome to session 25. I know there are a few people who really want the soundtrack for this class, so we'll see if we can talk to the producers afterwards. So you guys have some good party music for the weekends. We wanted to pick up a little bit and pick up where we left off with maturity last class. So what are we talking about with maturity? What's the basic concept here?
It's strength gain based on your time temperature curve.
Okay, so we can predict the strength development. We can predict the extent of reaction that's taking place based on a combination of time and temperature. So the basic idea is instead of just plotting things as a function of time, what we're going to do is we're going to put them on a new axis that's a function of time and temperature. Now, one of the things that we really need to be able to do is we really need to be able to describe this strength development. And there's typically a function that's used to do this. And the function that we'll talk about primarily is this function of S that you see here, where it's simply just sort of an S-shaped curve that we're going to actually talk about. You can pick sort of any response that you want, and we'll go through and we'll talk a little bit about this. You'll typically see a long-term value quantified, and this is typically our infinite stress term that we'll be talking about. So this is the strength at some incredibly long period of time. Now, there are a couple different strength models that are out there, or property development models. What you'll typically see used is something like a hyperbolic equation. There are two equations that are going to be used. There's the hyperbolic equation, which we can see listed here. There are other equations that are more exponentially related. The basic idea here is you've got the strength at any time divided by the infinite strength. So this is a number that is going to be a ratio between 0 and 1. So we're going to have the strength at any time versus the strength that you can get to at some long-term time is going to be related to this hyperbolic equation, which gives you the rate constant that we talked about last time. And the difference in time, typically the time being normalized to T0. T0 in this case is the time of set that we would normally be talking about. So you can use this hyperbolic equation to describe what we're doing. Here's a fit of the hyperbolic equation to a few different points. Again, you can see the strength term on our y-axis, time being plotted on our x-axis. The hyperbolic equation now magically sort of appeared on the screen. And we have our infinite value of strength, the long-term value that we're going to describe how we get that in a couple seconds. T0 being the time of set. This is typically going to be somewhere between initial and final set, but we could estimate that value. And the slope of the curve initially is going to give us some indication of our rate constant. And once you have this information, you can go and can predict the master curve and all the points that lie on it. Now, a few things that I will make mention of on how some of these properties are calculated. There is a program that will be placed up on the website. The program is referred to as, I believe it's ROD is the program, and I think it's rate of development. It's a program that a student developed here a few years ago just to go through the process of trying to get some of these parameters very quickly. The first thing that you need to do is you need to calculate this infinite strength. And there's a little bit of a trick that goes into calculating this, and I will point this out because it's a trick that you will actually use for quite a few other things. It turns out the software will actually step you through this process, but I want to point it out here very quickly. You will plot the strength versus the inverse of age. So the basic idea here is you've got the strength plotted on the y-axis. This is our strength value. On our x-axis, we've got the inverse of age, 1 over age, which basically means as you go out toward infinity, 1 over infinity tends to go toward 0 or a really, really small number, which means that the intercept is going to give you the value of the long-term property. One thing that I will point out in mentioning this is this entire curve is not always going to be a straight line, so you want to really focus in on the long-term data. 28-day, 56-day, 90-day data. That's going to give you a much more accurate prediction of the long-term strength than if you have all the data in the set. So a lot of times people say, well, I wanted to fit to all the data. You don't necessarily need to fit to all the data in the set. You want to fit predominantly to the later age data because it's going to give you a much more accurate indicator of the infinite strength. The other thing that you want to do is you want to calculate this rate constant and the maturity or the time at set. Typically here you're going to do a plot and you're going to do some different things on the axes. The x-axis is simply going to be age. The y-axis is going to be strength over strength infinity minus the strength at any particular time. All right, so that's going to give you a little bit easier indicator here. The slope of the line is going to be KT, and then you can actually use the intercept in KT to determine the T0 value, which should be very close to time of set. So here's some of the software. As I mentioned before, what the software is actually going to do is it's going to go through, put the data points, and it's going to try to fit a curve to this data. It's going to allow you to make some of these choices as which data you're going to use. Does the curve fit properly? Should you get negative times of set? It's going to ask you questions like that. Here you can see the infinite strength term it's going to give you, the time of set term that it's going to give you, and the rate constant term that you would get. Determining the reaction rate, simple way that this is going to be done. You're going to test specimens at different temperatures. Once you have those specimens at different temperatures, at different ages, you are going to simply plot this function, s over s infinity minus s, versus the age, and each one will have a different slope. That gives you indication of the rate of reaction when the concrete is stored at different temperatures. You can plot this out, and you will see that your KT value is now a function of temperature. So all of a sudden you can start to plot that, describing the activation energy concepts that we talked about last time, where you can plot your the natural log of the KT term versus 1 over the Kelvin temperature. The slope of that line is going to be this value that we talked about as EA, or EA over R, or Q. This is our activation energy. This is what we're going to start to use in describing the overall system. So now you've got the hyperbolic strength relationship. You can rearrange the hyperbolic strength relationship by replacing KT by this alpha KR term, where this is simply going to account for the different temperatures. So this will tell you that you get a different reaction rate depending upon the temperature that you're using, and the alpha is something that you would get from the Arrhenius type of approach. Okay? So if you test materials at different temperatures, they will all fall along the same line. Now, to take this a little bit of a step further, most people try to use this data and they try to combine it with some sort of a rate of development type of approach. So the one that is commonly used in many, many materials is the KJMA type of approach, which stands for these 4 guys whose names are up here. Some of them are easier for me to pronounce than others. Depending upon where you come to the field from, you will hear this either referred to as the Johnson-Mell equation if you worked mainly in metals, the Avrami equation if you were really into chemistry. Depending upon where you started out, each one of these guys sort of had the same equation that they were using, but they came to it from a different point of view. The real thing that this is related to in material science is the concept of nucleation and growth. So to take you back a step, and here's a little bit about all these different guys and what they were doing. But to take you back a step, a lot of times in steel classes or sort of more conventional material science classes, you will see an equation that looks something like this, where it basically tells you the fraction of the material that's transformed at any time is equal to 100% transformation minus the exponential of a rate constant times the time raised to some exponent. So K gives you an idea of the rate constant. N is an exponent that you're going to use to describe this response. And you get this S-shaped curve. 1 minus an exponential of a rate times time raised to a power gives you this S-shaped. Some of you don't see the S. See? It's a lazy S-shaped curve. All right, it's an S on its side. But the basic idea here is there's going to be some sort of a period of nucleation, and then the system is going to start to grow. You're going to start to see reaction taking place in the overall system. The cement, in our particular case, would start to be transformed over into a hydrated product, and it can be traced out on this particular graph. In steels or metals, you're typically looking at some sort of a transformation as you drop the temperature in the material. And what we're really looking at here is a phase change that's taking place in a metal, depending upon how long it's been heated or how long it's been cooled, how much of that transformation has taken place. All right, so many physical processes show this S-shaped behavior, and one of the great things is most engineers will try to jam this equation onto just about anything. All right, so you'll see a lot of people trying to do it. What you'll find out in cements is that it doesn't work real well at the real high degrees of hydration because we don't just have a nucleation and growth type of a problem. There are other steps and other stages that are taking place. Again, temperature dependencies you can actually work into this problem because you can replace that K term with this term that's related to our activation energy. So all of a sudden now you can describe this type of response at different temperatures, and you can say how much of my reaction has taken place, what's the extent of reaction. Well, it's simply going to be 1 minus the exponential. I now have an exponential term that corresponds to our temperature, time, and it's all raised to a specific power. Okay. As I mentioned before, the hyperbolic equation isn't the only equation that's out there. There are exponential equations that are out there, and these have been picked up and used by different people. Predominantly, you will see this one being used in a lot of the research that's coming out of Europe. This was Fries-Leben, Hansel, and Peterson's work out of Denmark. So instead of using that hyperbolic equation, they will use an equation that looks something like this. Again, M, A, and tau are things that are going to be fit to our overall response. What are some of the applications of this? So I'm not going to go into great detail on this. What do I expect you to be able to do with this type of information? I expect you to be able to look at a master curve. I expect you to be able to describe how the reaction rates would change as a function of temperature. And I expect you to be able to do some simple predictions from using a master curve. And you'll have practice with that on the homework. There's a couple limitations, as we talked about last time. We said that the hydration has to be enabled to be completed. Therefore, you need to have water in the system. The long-term strength may be problematic for materials that go up to real high temperatures early on because you don't get the same temperature. And we need to know the materials very well, meaning we can't change our mixture proportions. So it needs to stay wet because if our materials don't stay wet, hydration can't take place, and we're just going to have a bunch of old lima beans or a bunch of old grass seeds that started something and really couldn't finish it off. So we've talked about this idea of the fact that the microstructure can't develop. I think we covered this fairly thoroughly last class, again, on why it's a limitation. There are a few other things that I'll mention here as we go into this. The first is the option on how we would actually use this. Again, we talked about developing our master curve from concrete cylinders, using a field measurement, coming back with our particular maturity and reading off of strength. So that's that's probably the best way that we could use it. Here's an application where it can be used. It can be used in cold weather. Contractors, testing agencies, design engineers would use this. They decide where to put the sensors. You want to make sure that they're close enough to the outside edge if it's going to be cold enough that they're actually experiencing the lowest temperature that you're going to have in the system. Corners cool faster than the core part of the concrete, so you want to make sure your maturity sensors are out toward the corners. Look for critical elements, especially if you're using this to get rid of formwork, column connections, connections to slabs, critical materials, critical spots. You'll also want to make sure that you keep the equipment safe while you're using this in the field. It's amazing, but if you put something out there that looks like a box full of electronics, no matter what it is, somebody wants to take it home with them as a parting gift from the construction site. So you want to make sure that it's safe. There are also mysterious things that happen. We've had boxes out there recording temperature that have apparently been the best thing that you could shoot at while you're driving down the road. Maybe this is an Indiana thing, but I don't think that's the case. The other thing is these tend to attract construction equipment. So what you'll find out is you want to keep this out of the path of construction equipment. I can give you an example if you would like to see one of these data loggers that decided to battle it out with a 20-ton dump truck. The dump truck won, in case that was a question. It beat up on the little computer chips that were inside of these data loggers. So you want to make sure that they're tamper-proof, out of the way, so that they're not in anybody else's way. Older days are on lower budget projects. A lot of this would be done instantly on a spreadsheet. In fact, today, if you go out to paving jobs that they'll be using, they'll just have a simple thermocouple wire. They'll come out, they'll measure the temperature every 6 or 7 hours, plug this into an Excel spreadsheet. They'll be all set and ready to go. With the new modern equipment, it'll give you the information that you want. They will actually even program in master curves for you, so it'll just give you the information in terms of strength directly. But the theory is all of exactly what we talked about. One thing I will talk about down here, this is a huge caveat. I believe several people have gotten this wrong when they start to implement this. You are seeing people using maturity for acceptance, and what I would say is this is incredibly dangerous because errors in batching will yield the fact that you do not have the exact same material. If you don't have the exact same material, the master curve does not work for it. So you could have an error in batching, they forget to put in the cement, or they put in half of the cement, and it can give you a substantial difference in the overall properties that you can have. All right, so some of the applications, you're seeing a lot of people using this for mechanical properties, but there are also a lot of applications where this can be used to describe any property. Splitting tensile strength, pull-out strength, anchors, fracture tests, set time. Anything that develops as a function of time in terms of the concrete, the maturity method can be used to describe. But I will point out here that there are some significant limitations that I feel people miss out on quite frequently when they start to try to apply the maturity to a bunch of different things. And I'll talk about these. And these are what I would say are slightly advanced topics. There will actually be a paper that's given in China this year that talks about this. There have been a few students who've looked at very specific material properties that this could be a problem. One rate function doesn't necessarily always fit everything. And I'm going to put this into a caveat because in my opinion, in my humble opinion, if it is a chemical process that you are describing, the same rate constant should work because the chemistry is exactly the same for everything. What typically happens is people find different rate constants for compressive strength than they do for tensile strength. They find different rate constants for electrical properties, different rate constants for setting. And I would tell you it's typically because something else is going on in the system. The chemical reaction has one rate constant that's describing that. Now we can break it up and say it has a different rate constant early in the growth process than it does in the diffusion process, but in general it's going to have one function that can describe everything. Now I will talk very briefly here about one specific aspect where I think people get this wrong quite frequently. These are concrete pavements from Indianapolis. This is a typical concrete pavement. If you've been on 465 around Indianapolis, you have driven over this particular concrete. While you can't see it very, very clearly, what you can notice here is this is a concrete surface that's fractured at 0.75 days. For those of us who don't exactly know what 0.75 days in, it's really close to 18 hours. And what you will notice here is that when you fracture the surface, the coarse aggregate is typically smooth and shiny, and it pulls out. If you look at 36 hours, a day and a half, you will notice that the aggregate is now fractured. And again, this can't be said for every single aggregate, but this is a basic general trend. Before a certain time period, the coarse aggregate is simply pulling out of the system. After a certain time period, the strength has developed to a point where you start fracturing the aggregate. Now, we started to try to say that this would mean that you would have two different you would have to describe the maturity concept in a little bit greater detail. The maturity concept is telling you the extent of the reaction that's taken place. And frequently, we can relate the extent of the reaction that's taken place to other properties. So here you can see degree of hydration. The extent of reaction is determined here on our x-axis versus the flexural strength on the y-axis. And what you can see is if we just look at paste, the strength is very linear with respect to the degree of hydration. So if you just have water and cement together, the reaction that takes place, the extent of the reaction, tells you a lot about how much of the strength has actually developed inside of the system. The extent of reaction is directly related to the strength that's developing. If you look at mortar or you start to look at concretes, you will notice that this linear relationship no longer exists. And it begins to break down at a specific point, and in this particular concrete it's at about a day, where you start to go from aggregate that pulls out of the system to aggregate that starts to fracture. And it means that while the reaction is taking place here, the reaction is directly related to the strength that's developing. However, after that, the strength in the paste may still be developing, but your fracture is not necessarily going to live up to that. The aggregates are fracturing before you can break the paste. So you have a mechanism that's coming in and sort of short-circuiting the whole process. And this is one of the reasons why people see different rate constants happening in these materials. So again, concrete is takes a lot longer to test than it does to test mortar, so that's why you see different, less results there. Other things that you'll see, again, we talked about some of the motivation that people can be doing. Actually, before I jump into this, there's actually been some recent work where people have looked at this for electrical properties. And I will point this out, and I'll jump off of the slides here for a second and just comment on this very quickly. But when we start to talk about electrical properties, there are really sort of two issues that we're talking about in terms of the maturity method. One is obviously the pore structure is going to be refined. So here we're talking about doing something like either a rapid chloride permeability test or actually doing electrical sensing in the field. So there are two things that we're going to have. The pores being refined, and this is sort of the classic thing that we're saying is related to maturity. This is the component of the electrical measurement that says as the cement continues to hydrate, what's happening is the pore space is getting smaller and smaller. The ions are going into solution. So we are going to get a change in the resistivity of the concrete. The concrete is going to become more resistive because more of the pore space is filling in. There's actually a second component that comes in here, and it says that the conductivity itself is temperature dependent. Okay, so the basic idea is if you are measuring a solution that has ions in it, you are going to have a different conductivity when it's measured at a low temperature or a medium temperature or a high temperature. It's completely irrespective of what's happening with the refinement of the pore structure. So what you need to do is you need to actually set up a maturity function that is both a function of pore refinement and a correction for temperature. And next class I will bring in an actual plot that shows you this. I think that this is incredibly important because what you're seeing right now is people are trying to use rapid chloride permeability, use electrical measurements for durability assessment at very early ages. And there's a lot of people who are claiming it doesn't work. The technique works wonderfully if you do this temperature dependence. And I'll bring a plot that actually shows that for you so you can see it, because I think this is going to be another big change that you're seeing taking place in the future. Again, as we've talked about, in the lab, everything should be identical. That's the goal of lab work. You can spend a month and a half to get just 5 ounces of water or admixture into this beaker. In the field, that's not the case. You have some variation inside of the system. You need to be very, very careful on this because this is some actual data where we were trying to see could you use maturity and ultrasonic testing together to predict low-strength concretes. If you alter the water-to-cement ratio, your concrete strength changes. If you alter the aggregate content, it changes. So you can't just go changing the mixture proportions and using the same maturity function. So we won't go through that too much more. I want to jump ahead and talk a little bit about some of the aspects of mechanical properties. We will start the mechanical properties and we'll likely finish up on Friday right before spring break. One thing that I will mention about this is the last information that will be on the exam is information that's covered in this lecture and in lecture 26. So basically everything that's covered up till the time of spring break is information that can be on the exam. Anything after the exam, anything that we cover after spring break will just be on the final exam. So that gives you a little bit of a way to break up the information so that you know what's going to be covered. Right. Now, obviously, all of us came into this class excited about one particular concrete material property. And that was? Strength. F prime C. We all love F prime C. Right? We've all taken a reinforced concrete class, and the only thing that we know about concrete is F prime C is good. Right? We spent a lot of time talking about F prime C. Today is the lecture where we are talking about F prime C. All right? It is fantastically exciting. So what is compressive strength? Right? F prime C. All right? Compressive strength is generally thought to be the most important property. I would say this is true if your structure is going to fail in compression. If your structure is not failing in compression, this may or may not be true. I will say the reason that F prime C is so widely used is because it's easy. It's easy to test. It's easy to manufacture the samples. It's easy to put the samples in the back of your truck. It's easy to bring them back to the lab. It's easy to understand the test results. It's easy. It's straightforward. There's not a lot of thinking involved. So what the compressive strength test tells us is it gives us a general indication about the strength of the material. Gives us an indirect indication many times of what the water to cement ratio may be for our particular material or what class of materials that we're dealing with. And it gives us an idea about the consistency of the material that we're talking about. So many times on the job site, you may be pulling slump tests or cylinders, not because we necessarily care about the compressive strength, but because you want to make sure it's a similar concrete that's being placed out there. And if you get a very, very different compressive strength, you can say, whoa, wait a second, we got something odd going on. Somebody forgot to put in the cement. All right? Somebody added 50 gallons of water too much. There's a big problem out here. Right? But one of the examples of this would be a lot of states measure compressive strength for pavement. Very few pavements fail in compression. Most pavements fail in tension or they fail in something else. Right? The definition of strength, the ability to resist stress without failure, although failure is something identified with the appearance of cracks, it should be noted that unlike most structural materials, concrete contains fine cracks even before it is subjected to external stress. That's the ACI definition of strength. Maximum stress the material can handle. One of the things that is the most interesting to note about concrete is it will have cracks in it prior to loading. If you make a concrete cylinder, you set it out into the lab, you put a stethoscope on that and you record it over time, you will detect cracking. We do that. We use a very fancy stethoscope called acoustic emission. We listen for cracks. They exist. They're present. It is a composite material, so this happens. You will get lots of cracking even before you get up to the peak strength. And a lot of people will say, oh, my concrete's cracked. Is it a problem? Well, almost every concrete that's put out is reinforced concrete. And I will tell you that if your concrete doesn't crack, you could have saved a lot of cash by keeping the reinforcing to yourself. All right? Not putting the reinforcing steel in there. Because until the concrete cracks, the reinforcement doesn't do a whole lot. The real value of the reinforcement is when the concrete starts to crack. So we can look at a typical stress-strain diagram of our concrete. Here we can see the typical compressive stress-strain response. You will notice that the concrete is relatively linear and relatively linearly elastic, so it will load and unload along the same points, even though my drawing here doesn't necessarily look like it's loading and unloading along the same line. But up till about 40 or 50% of the load, it's pretty linear. After 40 to 50% of the load, all of a sudden you will see that the line starts to deviate from linearity. This deviation is cracking. It's all due to the microcracking that's happening inside of the specimen. It will hit a peak load, typically corresponding to a strain of somewhere between 2,000 and 4,000 microstrain. And then you will get a strain softening response where the strain decreases as a function of time as the crack begins to open up inside of the material. Now, a few things that we can say about the cracks that are developing inside of our concrete. The shape of the crack is a direct indication of how much composite action you have acting in the system. These are the stress-strain diagrams or stress deflection diagrams up here towards the top. All right. On the bottom, you have a picture of what the concrete looked like when it actually failed. So this isn't really, even though this looks cartoonish, this is an actual PhD research. The only thing that I've actually done here is instead of using the actual pictures, I drew my own versions of what the cracks looked like. When you're testing a paste specimen, it is very linear up to peak. From peak, the load drops off very, very quickly. The shape of the crack is very linear, straight up and down inside the specimen. So this is being compressed in these directions, cracked straight up and down, top to bottom. And I'll talk a little bit more, but this had no friction on the top and no friction along the bottom surface. As you start to add a little bit of aggregate into the system, you add a little bit of sand, what you will notice is the stress-strain response changes a little bit. The post-peak response doesn't drop off as dramatically, drops off fairly quickly, but you start to get a lot more softening behavior. The curve changes a little bit. That curve change is directly related to the types of cracks that are forming. No longer are the cracks necessarily straight up and down. They start to get a little bit of tortuosity. They start to get a little wiggle to them. The real idea here is all of a sudden the crack is having to start to move around those sand particles. As it moves around those sand particles, it starts to consume more energy before it starts to fail. By the time you've moved up to concrete, you can see that we've got quite a bit of nonlinearity in this pre-peak region. You also have quite a bit more softening response, and you see the cracks are much less linear. There's a lot more branching. There's a lot more movement. And this is because all of a sudden the cracks are starting to interact with the large aggregates, having to go around the larger aggregates. So the basic idea here is as you add aggregate to the system, the strength will typically go down a little bit. But what you're actually doing is you're providing ways that you are going to consume more energy in the overall system. You're going to make the system less brittle by making the crack work its way around these different aggregates. The more tortuous the crack path, the more wiggly the crack path, the more energy that's been consumed as the crack grows across the sample. So this idea of the behavior of compression can be broken up into 4 parts. Cracking at the interfacial transition zone. This may be occurring up to about 30% of the peak load. Between 30 and 70, you'll see a lot more interfacial cracking. As you get above about 60, 70%, all of a sudden this interface cracking is going to start to link up with other interfacial cracking. So you're going to start to see these cracks beginning to localize, beginning to get pockets of cracking that starts to develop. By the time you get into the post-peak region, you have one single crack that is opening. The rest of the material is actually unloading, and the cracks are actually closing. So all the damage is going to be localized into one particular spot that you are going to see as the visible crack that's on the surface of the sample. All the other cracks are going to sort of go, when I say go away, they're going to be non-active cracks. They're not going to want to grow. They're going to start to unload. They're simply going to unload in the overall system. Now, one of the other things that I would like to point out here is there are a few assumptions that we typically make, and we sort of blow by these assumptions when we do every other class that we've ever taken. And one of the things that I want to point out, and this is taken out of Timoshenko's book, and for those of you who don't know who Timoshenko is sort of a very famous mechanics of materials person, strength of materials person, and he has sort of a classic book on elasticity. And it is sort of the reference book that most people say on elastic materials. And most of what we do in engineering design is sort of based on the elastic solution or some modification of the elastic solution to account for inelasticity. In the preface of Timoshenko's book, he starts to talk about some of the assumptions that are made throughout the course of that book and throughout the course of most of mechanics. And what I've done is I've put this in here. This is a fairly common mechanics position that's taken. He says a whole bunch of stuff, and then he says it's going to be assumed that for the matter of this book, the elastic bodies are homogeneous. They're homogeneous. It is one single material. For the most part, the bodies are isotropic, same properties in all directions. And then he goes on to say, while I'm assuming this, to make the math a whole lot easier in this book, structural materials typically don't fall into this class. Steel doesn't fall into it, aluminum doesn't fall into it, concrete doesn't fall into it. These assumptions can be violated. These assumptions hold true as long as the geometric dimensions of the body are large and the response is uniform. So what he's basically saying is if the size of the specimen that you are testing is much, much bigger than the size of the aggregate, then you can assume the entire system is homogeneous. So if you have something that looks like a dam, 60 feet across, and you've got an 1.5 inch aggregate size, the aggregates are so small that the entire system looks homogeneous. You are on the macro scale. What I will point out here is that very frequently in the lab, you are not on the macro scale. You are on the meso scale. The aggregates are on an 1.5 inch, 2 inch size that you're looking at. The whole system is only 5, 6 inches across. So that means your particles are 20 to 25% of the smallest dimension. This means that you can actually get some very odd behaviors, and we'll talk about some of these. The other thing that I will point out here, and this is a much more subtle thing that he points to, and this is my say no to strain comment. Okay? We are very anti-strain today. The basic idea that he assumes here is that you have to have a uniform response. Now, what I have just stated says that up until peak, you have microcracking, it's distributed throughout the body, you can have a relatively uniform response. Strain may be a valid concept on the global scale when you start to look at concrete. Where this starts to break down is the last part of what we talked about here, where we said you have a crack in the material that is behaving very, very differently than the uncracked material. So you have a material that's uncracked and unloading. You have a piece that's cracked, softening, and getting bigger. And that's what you see in this softening curve here, which means that you can't simply describe this in terms of strain. There is an issue here because the deformations are not uniformly distributed throughout the entire body. We'll look at a few examples of this as we go through the rest of the lecture. So here we can see sort of a picture of this idea, a picture or concept of this. You're seeing a localized damage region developing. This is what we typically refer to as a crack. Localized damage region is what we're talking about as a crack. You see cracking at the interfaces. All of a sudden you start to see those cracks coalescing. Then you see the crack opening, a single crack opening while the rest of the material is unloading. Now, a few of the things that we'll talk about as it relates back to testing. As the strength of your concrete starts to increase, you will start to see a different response in the overall concrete. All right, so this is information that comes out of a PhD thesis. And this is a thesis that was specifically looking at topics that are related to how the strength of the concrete influences the stress-strain behavior. The region, the proportion of this line that is linear, becomes much, much bigger for the high-strength concrete than it is for the normal-strength concrete. All right, so to give you an idea, this is about a 5,000 psi mix. This is about a 10,000 psi mix. This is about a 15,000 psi mix. To put those in units that we may be a little bit more familiar with. Okay, this is an incredibly high-strength concrete. This is a good quality concrete. This is something you're going to see every ready-mix producer doing. The portion of the diagram that is directly linear, here you might see it might be 50% for your normal strength concrete. For your high strength concrete, it's much, much larger. 80%, 90% of the system is linear. The other thing you'll see is the strain at peak. We all know from our ACI 318, the strain at peak is 0.003. And what you will find out is that the concrete doesn't always behave that way. That is a big assumption. You will see numbers anywhere from about 2,000 to about 5,000. If you were in the UK, it wouldn't be 0.003, it would be 0.0035. All right, and it comes in that this is an approximation that's used to smooth out a lot of these different behaviors. All right. The other thing you'll see that's a big difference is you will see the normal strength concrete tends to have a much more gentle slope after peak than the high strength concrete. And in fact, the student who was doing a lot of this work, the whole thesis was on how you control the behavior of the concrete when it fails. Because it becomes so brittle when you get to these high strength numbers that you have to go through very, very specific types of testing. And what he was doing here was he was actually using something like a bicycle chain around the concrete to use circumferential control to control how fast the circumference of the concrete was changing so that he could actually get the entire stress strain response. This is also accounted for in your ACI 318. Does anybody know how the shape of the post-peak behavior is accounted for in your design equations? Oh, that's a good question. That's a good exam question. No. Much more subtle. It'll come in a little bit in some of the limits. But if you remember, you start off and you start doing your calculations, and you have to determine these coefficients for the Whitney stress block. There's an alpha coefficient and a beta coefficient. And if alpha is greater than 6,500, or the concrete strength is greater than 6,500, then alpha is 0.6 or something like that. Right? And there are all these different rules. Those rules are their best way to make Whitney stress block work for these stress strain behaviors. That's how they're accounting for the brittleness in these particular materials. Okay? That's where that's coming into the code. Pre-peak and post-peak properties, obviously as you increase strength, we talked about it becoming more linear. We talked about the post-peak dropping off. When you put fibers into the system, fibers don't increase the strength. Until you get to a certain volume, the fibers don't really do anything except they will alter the post-peak response. They will alter the toughness of the system. All right, so here again is a little bit to talk about some of these testing issues. We'll talk about them very briefly. This is a study that was actually done here where Sunil actually used microphones on the concrete and used LVDTs to try to explain some of what we're looking at. These results are not part of Sunil's work. This is part of a PhD thesis at Northwestern as well as a Rylam report. What you can actually look at here is if you look at the strength of the concrete or the normalized strength versus the size of the cylinder, or the normalized strength versus the length to diameter ratio of the cylinder, you will notice that you do not get the same strengths for all of these different geometries. Now, for some of you, this should be a huge cause for concern. Because what this says is it says that the size of the structure that I'm testing or the size of the sample that I'm testing gives me a very, very different strength. Therefore, how can I use a 4x8 cylinder to describe anything that I see in practice? What I will point out is that this is this data is true data. However, it points to a problem with testing. This type of data corresponds to testing that is not very carefully done. And the big issue here is the idea of end restraint. If you have platens on your specimen, on your machine, so you can picture this as the big steel platen, you've got a hydraulic cylinder that's pushing down, you've got something that's pushing up, and this is your concrete. If you don't do anything, you will have friction at the end of your concrete cylinder that keeps that edge from expanding. The steel and the concrete do not have the same Poisson's ratio, so it will restrict the concrete from expanding. When you do that, you no longer have a state of uniaxial compression at the ends of your sample. You get a much more complicated state where you have biaxial or triaxial states of stress. Now, when you get a geo material that has confinement, you completely change the behavior of that material. You think about it with sand. You step on a pile of sand, the sand sinks. You take that exact same sand, you put it in a bucket, you apply some confinement, there's a lot more resistance of that sand. Here, you're providing confinement at the end of the samples. So one of the things that you will hear people talk about a lot is, did you get a cup cone failure at the end of your sample? Well, that cup cone failure has little to do with the concrete itself. That cup cone failure has to do with the fact that this is confined concrete. This concrete is trying to bulge out and wants to spall off of the edge of the sample. So what you could actually do in a perfect world is you can reduce the friction at the ends of the samples. If you reduce the friction by using Teflon on the platens, or by using brushed platens, or by using any of a variety of different techniques, what you can actually do is you can get rid of a lot of these effects of specimen length, specimen diameter, and you can get a strength that is relatively independent of the size to length ratio. Now, not everyone is going to use frictionless platens. So how do you start to utilize this information? What does it tell you? Well, it starts to tell you an idea of why, and I don't know why my numbers are slightly skewed here, but 2 should be right below this thing here. All right. It starts to tell you why we use a height to diameter ratio of 2 when we test a concrete cylinder. At a height to diameter ratio of about 2, you get a fairly good measurement of what the results would be if they were frictionless. Right? Gives you an idea of why we keep the height to diameter ratio constant. Also gives you a little bit of an indicator of what size platens we should be using, things like that. Now, you may say, well, where would I ever use this? It is not infrequent to have something go wrong on a job site. Someone says, well, we lost the cylinders, they were shot at, I tied them to the bottom of a motorboat. We have no idea where the concrete cylinders were on that particular job. How would we know what the strength of that concrete is in situ? Well, let's go out and take a core. So you go out to your 4-inch industrial slab and you take a 4-inch diameter core. And you trim off the ends and you bring it back to the lab. Now you're testing a cylinder that's 4 inches tall with a 4-inch diameter, which means it has a length to diameter ratio of 1. You would expect to get a higher strength unless you do something to account for the ends. All right, so you need to be very careful when you start using these types of altered specimen geometries for failed materials, that you properly account for things that could overestimate the strength in the system. All right, when you reduce the friction at the end, I've shown you some nice little pink Teflon here. I don't know why it's pink. It used to be a different color. But the basic idea is the Teflon sheets will allow expansion and contraction. You keep a uniaxial state of stress, and it means that you have a crack that goes straight up and down inside of the specimen. All right. There's no longer that cup cone failure. The crack goes straight from the top to the bottom of the sample. Now, what are some of the implications of this? And I'm going to say this, and it is going to shock the foundations of the world that you knew. Stress-strain is not a material response. The stress-strain response that you get of concrete is not a material response. It depends on the geometry of the sample that you have tested. Now, up until this point, you have been blissfully happy using the stress-strain response in all of your 473 types of problems, 573, 576, 671, oh my goodness, all that reinforced concrete design. But the stress-strain diagram that you are using depends upon the length of the sample that's being tested. So now, if you have a short specimen, let's imagine something that is short and fat. I like things that are short and fat. I tend to be short and fat. Right? This response of the short fat cylinder is going to be very different than the response of the tall cylinder. This is just a trace of real data. You can see the long specimen's stress-strain response, the short specimen's stress-strain response. Up until peak load, they're very similar. In the post-peak region, they are very different. Why are they so different? Well, it's one simple idea, and it's the concept of localization. Damage localizes into one particular region. That region is the same size irrespective of the specimen length. So when you normalize it out or you average it out, it tends to play a bigger role in different size specimen geometries. We will pick up here on Friday where we start to talk about some of this in greater detail, and we'll start to talk about this type of model.